So, where we left off last time was talking about bad clicks, and we're all done with that. Now we're into the next topic, which is APIs. So, application program interfaces or programming interfaces, those are the mechanisms whereby different applications share data. So, an API, it's an interface between applications based on standard input and output formats. Okay, so to have those applications communicate, basically you design some generic object conforming to some kind of standard. For example, way back when in transaction systems, we were talking about a credit card transaction. So Amazon, if they want to see if some credit card transaction goes through, they have a standard object of what a credit card transaction is. The card number, expiration date, security code, maybe the list of items if the credit card wants to do fraud detection. Bundle all that together, send that out. That's the standard object, and that's what the credit card application will be designed to receive. So when we talk about interfaces, we just mean a way where two different applications can communicate, and the way they can communicate is that they're exchanging data in some standard format so that you know the inputs are going to be correct. Nice thing about APIs is the designers of these applications and their interfaces, they don't need to know any kind of machine-specific details. For example, if we're doing an ad application interface, right, then the two applications are, number one, a web browser, and number two, some database system that's serving up ads to be displayed on those web pages. The database doesn't need to know what kind of operating system you're running, what kind of browser you're running. All it knows, if it serves up an ad in a standard format, the browser will correctly handle the details of displaying that ad. Okay? That's APIs. So, ad APIs pull these online ads from a database to appear and act in some kind of standard format. Typically what you'll see, right, maybe some labels, some other text. There'll be a format for size. How big is the ad going to be? What's the image and video quality, right? So what is it going to be, an MPEG? Is it going to be a WMV? Is it going to be something else? How big is it going to be? How many frames per second? All that. And then last, the action on click, right? So if you click the ad, what happens? And typically, it's going to take you to the website, right? So if it's an ad for, I don't know, free tires, free donuts, it's going to take you to the website where you can get free tires or donuts. Okay. So, for API formats, the formatting essentials, number one, description of the object itself. So basically, the data it can hold and all the actions it can perform. That's what defines an object. And then the format for the inputs and outputs. So number one, the things that it's going to have, and number two, the format that it's going to be in. For example, is it just plain text? Is it numbers? Right? You get the idea. Now, two ways to do it that we've already discussed. XML, you can use XML, but it's kind of out of date, not very often used anymore. Or JSON, which is that more compact one, right? So XML is a lot like HTML. It's kind of bulky, uses opening and closing tags. JSON is a lot more compact, right? Doesn't need those closing tags. Okay. So we talk about object description languages back when. This is what you're using to define the content of the object. All right. Now, ads as objects. Surely many of you have sometimes looked at a product on Amazon and then like a few minutes later or an hour later, you go to another site and you see in the Marts there, holy shit, there's that ad that I just looked at. How did that happen? Right? You guys have, yeah, you've seen this. Okay, well, basic process, Amazon has a standard advertising tool, right? They have Amazon ads. Websites can agree that they're going to display ads for Amazon. So, standard inputs, going to be some kind of user history, right? User history will include items recently viewed, or better yet, items recently added to a shopping cart but not yet bought. So things like that. And then the application can grab data from a cookie. Cookie's a little data file stored on your computer. So actions, number one, pull the current ad image, right? So there's a window on the screen where the ad can be displayed. It's going to pull the ad from the database, figure out which one to do, then display it. And then clicks, typically for Amazon ads, if you click on that ad, it'll lead you to that particular product page. And then the outputs, right? Number one, there can be a response or a non-response. So if somebody responds to the ad, if they click on it, then that's something that gets notified. If Amazon never gets a notification that someone clicked on the ad, that counts as a non-response, right? Basically, if it waits for a while and there's no response, then Amazon says, yeah, okay, we're not getting one, we're going to mark that as a 0. Okay, and when something gets clicked on, Amazon can also use that to update the cookie and affect future ad displays. For example, you've been to Amazon, you've looked at, I don't know, baby carriages and bookcases, and you didn't buy either one. So you go to some random web page, say Amazon picks the one that they think is going to be best. They say, well, baby carriages, you know, because anybody can buy a bookcase anytime. But if you're in the market for a baby carriage, we want to get you that right now before you buy one somewhere else. So they show you the baby carriage. Now, if you go to Amazon and then you subsequently buy that baby carriage, right? Amazon wants to update your cookie. They want to say, okay, now you bought this thing, so next time you go, maybe we'll show you the bookcase instead, right? Because there's no reason to show you the baby carriage ad twice. Does that make sense? Okay.
So that's how they suggest that they are, oh, I just talked about that. It's not that they're listening in and it's going to.
Well, you went on their site. Yeah, I mean, they're not stalking you, you know, but yeah, basically, we'll talk more about cookies in the YouTube module. But yeah, essentially, other sites, non-Amazon sites, have partnerships with Amazon where they agree to display ads on Amazon's behalf. It's not like the whole internet is out to get us. Yeah. Yeah, exactly. Okay. So, databases. Now, Google has a whole bunch of databases. So we're going to talk about databases now. That's what there was to say about APIs for now. So Google has lots of databases, right? For advertisements, for user response to ads, to search results, cached web pages, web analytics data, lots more. They have a whole lot of databases, right? They're a very big operation. Now, perhaps surprisingly, Google's advertising runs on an extended SQL system, right? What Google calls NewSQL. So the base platform is Spanner, and on top is F1. F1 is the database that holds all the ads. Now, for all these databases with Google that I'm going to talk about, you don't need to know all the inner workings. I'll give you some of the inner workings, but basically you need to know what databases Google has and what they're for. Okay? All right. So, first thing, we'll talk about joins. So, main advantage of relational databases is permitting join operations. Join operations are any time that you take data from two different tables and somehow integrate it, right? So when you were doing your SQL queries and coming up with stuff like, show me all the students who have registered for this class and have gotten a B in the grade list, whatever. You integrate data from across tables, that's a join operation. Okay. Problem is, in some cases for joins, they can be multiplicative. Essentially, you're taking all of the possibilities in one table and multiplying it by all the possibilities in the other table. Basically, the amount of data that you have to consider becomes essentially the two tables multiplied by each other. Very big. So, if you have a very large table, right, with 1 million records in table 1, another table 2 with 1 million records, if you do this kind of what's called a full join, outer join, basically you end up having 1 million times 1 million is 1 trillion comparisons. Now, when I say that these things run very slow, you could do 1 million comparisons on one machine in RAM in a split second. Doesn't take very long at all. However, 1 trillion comparisons, even on one machine, that's going to take a little while. But chances are, you're not going to be able to run that trillion comparisons on one machine. What's going to happen is you're going to have it blow up and become multi-sharded. That whole giant mega table is going to be distributed across a bunch of servers. And if you don't have a system specifically designed to deal with that, it's going to be very slow because all the comparisons back and forth between the different machines are going to happen at network speed, at signaling speed, not at RAM speed. So all that stuff, takes a little while for one machine to send a notification to another, that little tiny split second. It's basically going to be multiplied many, many times. So what often happens is you have this breakpoint for large tables where a business says, okay, all the stuff that we're doing, I can run it on one machine. It's super fast. And then they hit that breakpoint where it starts to get distributed over multiple machines, and suddenly everything gets really slow. Okay. If you're interested in more, the Stack Overflow article. If you're a tech person generally, Stack Overflow is your friend. That should be part of your daily random Googling. They have a lot of good tech-related stuff in there. But this one, why do joins reduce scalability in large-scale distributed database systems? Yeah, this is assuming it's still active. I haven't checked on it in a while. Assuming it's still active, it's a very nice discussion. There's some good intelligent responses there. Okay, so I'm going to see about that. Anyway, joins can happen faster in some cases though. For example, if you combine everything into one single new table, it can be stored on one machine, or if you can partition the data into some kind of matching subsets. For example, suppose you have one very large table, but the different aspects of that table, let me give an example. This is basically the same thing we talked about a minute ago. Sorry, something's gone real wrong here. Okay, but the good thing is, okay, so yeah, the Stack Overflow article is still there. Basic idea is this: if you have a big table, and suppose you have some kind of, customer data by, I don't know, zip code, okay? If it's all distributed randomly around in there and you want to run a query on that, if it's indexed by name, not by zip code, you're going to have to search through the whole table. However, if you can do this, if you say, well, we know the zip code is a common search parameter, right? Something that we're looking for. So it makes sense. We're going to pre-sort the data by zip codes, right? So whatever, I'm going to put in some numbers. All right, so 60601, 60602, dot, 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 60, I don't know, 699, whatever, okay? Yeah, point is, you have a very small group. Now, even though the table might be very large, if you know that your query is only concerned with that tiny portion of it, then you can, again, solve some of the problems with multiplying big tables together in table joins, okay? But if it's all scrambled randomly, if it's only indexed by last name, the zip codes are going to be scattered around everywhere, and you're going to have to search through everything. It's going to be very slow. Okay, like I said, that's kind of techie. So what's the key takeaway about this? Key takeaway is this: relational databases are nice if the data is all the same style. Under certain circumstances, they can be fast. They allow you to do queries involving multiple tables, but if the tables are very big, then those queries can run so slow they may not even be worth the trouble. You got to design your databases smarter, and essentially that's what Google is doing. Okay? All right. So Spanner is Google's big base database. Everything that Google does pretty much is built on top of Spanner. So Spanner is a system that uses SQL but approaches NoSQL performance levels. Basically, it allows a lot more flexibility. It's kind of a middle ground. It has, a lot of the good consistency guarantees of a SQL database, so it's suitable for transactions, but it has more flexibility, so it, doesn't, it's not a complete nightmare to change database fields, for example. Okay, so key point, provides almost immediate consistency as a distributed system. What does that mean? Well, if you have multiple copies of your data, it's still going to keep them consistent. For example, you're running transactions, you have, again, different copies of your data for whatever reason. If a transaction happens, you want all of those pointing in the same direction. For example, if you got the money, the goods should be going out. If you didn't get the money, the goods shouldn't be going out. Okay? So it has, for any kind of transaction system like that, consistency guarantees have to be very strong. Okay? But it can do this. Even though it's, it has some NoSQL type attributes, it can work well enough to be a transaction system. So the other thing, as a cloud tool, nice thing about Spanner, businesses can migrate their databases as is, because even though Spanner allows an extended SQL, it still processes all the ordinary SQL commands. So if you're some business, you want to import all your data, upload it all into Spanner, you don't have to change any of your database operations. Everything is written in SQL instead of Google's NoSQL. That's fine. Spanner handles SQL just fine. Okay? All right. Excuse me. Okay, so image here, difference between consistency, speed, and flexibility. Okay? So, consistency. Basically, traditional relational database systems offer strong consistency guarantees. If something changes, the rest of the world is going to get put on hold while the system makes sure that everything is correct. So, it'll be, all the data involved will be consistent, but it might run slow as the system gets big. Okay? Spanner also provides strong consistency guarantees. That's why it's over there. So, but what it also does, it allows more flexibility. So when I say facilitate schema changes, if you want to change the structure of a database, right, if you want to add some new fields or change the format of a field, it's relatively easy and painless to do that on Spanner. much more so than it is in a large-scale traditional relational database. Because remember, relational databases, everything is carefully calibrated to run well, right? So when the system is saying, I know exactly how long a row is, I know exactly how long each column is, I can very quickly find where something is just by using offsets and indexes. Well, Spanner uses that same kind of mechanism, but it's also geared to allow things to be changed and updated very, very easily and quickly. So again, Google's system, they're constantly updating their database for web pages. One business's relational data is going to be kind of trivial for them. They can do that pretty fast. All right. Down here at the other side, maximum speed and flexibility. So, basic thing with NoSQL systems, for many kinds of operations, NoSQL is going to be faster. One reason, right? Imagine if you're doing document storage and a document doesn't have a standard framework. It's going to be a nightmare to set that up in a relational database, and most of your data is just going to be a bunch of zeros. So anytime you're scanning through everything, it's going to take a long time to find it, right? NoSQL systems, yeah, you don't have that ability to, guarantee that every record has every field, but if you want to find a particular field quickly, it's very quick and easy to do that. The other problem, typically NoSQL systems give up some consistency guarantees, right? We talk about eventual consistency a lot. Yeah, if you're doing something that you don't care that much about the numbers, like Facebook likes on a picture or the precise rankings of search results, some inconsistency is tolerable, right? I mean, you don't want it to totally go off the rails, but not every little tiny detail has to be perfect like it would in a transaction system. So that's essentially the trade-off. NoSQL systems, very flexible, and in some cases greater speed, but what you give up primarily is the ability to do table joins, okay? Or you can do them, but they'll just be nightmarishly slow. Okay? Traditional relational database systems, strong consistency guarantees, but they're not going to be flexible. If you want to change something, it's a real pain in the ass to change. So Spanner tries to get the best of both worlds. Gives you some extra speed and flexibility while maintaining strong consistency guarantees. Okay? Questions? All right. So let's talk about the databases. Number one, F1 is Google's database for storing ads, and as you might guess, a very, 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 very big relational database. Now, in a sense, this works as a relational database because Google can say, if you are going to run an ad with us, it has to have a specific format. And even if Google is allowing a variety of formats, right, so it might have, 10-second video ads, 20-second video, 30-second video ads, whatever, it can store each of those in different tables, so it can ensure within each table the same kind of ad, right? So the problem of, this video record is very large and some are very small, by segregating the different video types into different tables, they can largely get around that. We'll talk a little bit later, too, about YouTube. YouTube adopts a different approach for storing videos. So, number one, highly consistent, despite being large-scale and distributed. Number two, like NoSQL databases, it's scalable to run on many instances of separate standard hardware. So Google has a whole lot of ads. There's no way you're putting it on just one machine. It's going to be very big. Google has a whole bank of servers dedicated to that, and it's designed to run pretty fast, even though, many different ads could be in different places. One of the things, for example, is that groups of related ads can be stored together. So if somebody does a search for a particular category like, winter boots, a lot of ads for that are going to be grouped together so Google can check them all out, pick which one it's going to run very quickly. Okay. Operational properties of F1. Number one, how many times do you think an ad is viewed versus how many times it's uploaded? Yeah, right? For every time you upload it, hopefully it's going to be viewed thousands or millions of times, right? So, write speed, the ability of the advertiser to upload that data to Google, that doesn't have to be fast. We don't really care. You only do that once. If it takes a little while, if it takes a couple minutes instead of a split second, so be it. Read speed, however, that's got to be super fast, right? Because Google wants to deliver the search results super fast without having ad retrieval slowing it down. So, reading should not materially interfere with search result speed. Write speed, less critical. I would say not even really important, right? You think these advertisers are going to say, oh man, it takes us like a minute 30 seconds to upload our ad to Google, but with Bing it only takes a minute 15 seconds. We're putting all our stuff on Bing now. No, that would be insane. Okay? Anyway, based on Spanner and Bigtable, we've already talked about Bigtable, but yeah. Okay, so that's a little stub that's not really relevant anymore. I shifted some stuff around. Okay, so F1 runs on Spanner. Second thing, BigQuery. So as you might guess, BigQuery is a Google application that allows fast queries involving very large tables. You might even say it involves very big queries. Okay. Now, a couple of these links, I know some of these went away, but I'm always hoping they'll come back. So the good one, the one I want to see here. Okay, let's see how this still survives. Oh, it's still here. Okay. Yeah, so this is a thing, basically talks a little bit of detail about how Google's BigQuery runs successfully. I guess I updated this to get rid of the link that doesn't work. So the short version, organizations often find that under their limited hardware, their poorly designed system, or their less scalable systems, they can run queries that might take literally might take days to return the results. With BigQuery, any result that it can run has to be retrieved within 30 seconds. So quite often businesses will find they can't run the queries on their own hardware, they bring it to Google, Google arranges the data better, boom, they have no trouble delivering it in 30 seconds. Or in some cases, they group the queries, they rewrite the queries to run differently and in parallel. For example, right, suppose these two sets of records are very large. For zip code 60601, 60602, suppose that they're sufficiently large that if I try to run a query, damn it. Okay, if I try to run it like this, maybe it takes a very long time because these two particular zip code segments are huge. So what businesses might end up doing is say, okay, that failed, so let's break it down a little bit. Let's break it into two more. All right, so then select from okay, they might rewrite their queries in basically some kind of simple version like this. So essentially, they've decomposed the problem. In the first case up here, right? In the first case up here, I have both zip codes included in the query. Maybe that's too large. But if I break it up into these two, right, where they're two separate queries, and at the end I just sum up the results together, that might be perfectly fine. Okay, I get all the same people, but I run it just fast enough that it gets under BigQuery's 30-second limit. So that's kind of the stuff they do. If we had a little more time, I could talk some more techie things, but that's all right. If you're interested, you can look stuff up. Anyway, BigQuery is a very useful specialized system. So for most businesses, just joining Google and paying a little bit extra to use BigQuery, vastly cheaper than building a similar proprietary system from scratch. One of the things, if you're a very big website and you're gathering a lot of web analytics data, Google has one analytics platform called Google Analytics 360, and you pay 150 grand a year for that. If you're a very big business, 150 grand a year is nothing, right? It gets you access to BigQuery so you can crunch all the numbers for your web analytics. And again, way, way cheaper than designing your own system. You just show up and use Google's. Most businesses, even big ones, they don't want to be in the data management game to this scale, right? That's not what they do. They make cars or they make shoes. They don't want to be full-time data people, okay? Downside, of course, even BigQuery has its limit. If the data gets too big and the query and it's stored haphazardly without any real grouping within tables, yeah, might not work so well anymore. One of the key problems with something like BigQuery is you might need to have the same data in different tables, but indexed in different ways or grouped in different ways so it's easy to find. But again, technical stuff. All right, here's a couple examples though. Suppose you have one table that's large, even insanely large, like hundreds of millions of records, and one is pretty small, like a few thousand, right? If you were doing some kind of multiplication, right, if you're doing some outer join where you're like cross-checking everything in every table, it might still take a very, very, very long time to run that. However, Google can run queries on this Essentially what they do, take that one very large table of 100 million records, divide it into slices of, say, a couple million records each, and pair it with the one small table. So every machine has a slice of the big table plus the entire very small table, which becomes negligible when the big table is big enough. And then essentially processes like MapReduce that we've talked about before. At the end, Google compiles and returns the query results, right? Basically, it runs the query with the one slice of the big table along with the complete small table. You end up with one slice of the query results for each pair. At the end, you bundle them all together. Another possibility, if both tables are large, essentially what Google would have to do is make a super large table containing all the fields of both, right? In the worst case, you'd have to multiply the two tables together. And essentially, you're going to have to do that by breaking it up over multiple machines if it gets big enough. But again, if your tables are big enough and you really are multiplying them together, eventually the super large tables do get too big for Google to handle. So let's see what this handles here. Yeah. So this one is no longer, we'll see. Yeah, that one is no longer there. There used to be an article about very large table joins and basically how big they had to be before BigQuery started to fail. It was an interesting little article, but that's okay, we can skip it. Okay. So big picture stuff, difference between BigQuery and Spanner. They sound similar, kind of. BigQuery can process a lot of data quickly, so can Spanner. So what's the difference? Well, Spanner is good for a lot of frequent but fairly small database operations, like transactions. Somebody buys something, database record gets updated, right? That's relatively computationally simple. BigQuery is good for relatively infrequent but truly massive database operations, right? For example, you have like an exabyte or you have many petabytes of data anyway. You want to run some query on that. Spanner, just by itself, is not going to be the ideal system for that. Spanner is geared more towards smaller computations. BigQuery is what you want for that, okay? So, again, Quora article. What's the difference between Google BigQuery and Google Spanner? When is one preferred? Again, Spanner is good for if your system has a lot of small database operations like transactions. BigQuery is good if you every now and then have to run a really massive query. Okay. All right. So again, what you should know, take away from all this, and we'll cover it again before it's all over, right? Number one, you should know what a database join is, and that's basically where you're involved in a relational database where you're looking at data from multiple tables, right? So a query that looks at data from multiple tables is doing a table join. Second, what is Google Spanner? Spanner is Google's base database platform. What are the things about it? Well, it's more flexible than a relational database, provides better consistency guarantees than typical NoSQL databases. Okay. Ta-da. F1 is Google's database for storing ads. You should know that. Number two, BigQuery. As you might guess, right? System for allowing queries on very large tables. Okay. And understand, the things that they're good for. Okay, those are the key takeaways from that stretch. Okay. Questions on any of that? Yeah.
I was going to ask you about you talked about it in the article.
Okay.
Is there a limit? Like, does Google let these people know, let their clients know? Like, by the way, our queries can only handle.
Oh no, it's an experiential failure. So what'll happen is you have a query that you want to run. Google will try to run it. If it takes longer than 30 seconds, Google will say, "Sorry, your query was too large to run, even on our massive system. Please somehow break it up." And then you can do like the thing I did with like breaking up the zip codes or some other format. Or you can re-index your tables and only use a group, right? So one extreme case you might do, right, if it were really an issue, instead of having segments of data within a table, you might set up these as being entirely separate tables even. So there's different strategies organizations can use. Same thing, Google internally could break up the data that way. We don't know all the special sauce that Google uses, but basically it tries to arrange the data smarter. But again, eventually, if there are enough records, even BigQuery is going to say, nope, sorry, longer than 30 seconds. Yeah. Okay. So then, moving on. Terms and definitions. So, data marts, data warehouses. So, a data warehouse is all the data belonging to a business organization. Think of it as they have a warehouse, which would conventionally be for physical stuff, but now it's for data, okay? So the warehouse is shared by the entire business. A data mart, for some reason they chose this term, right? A data mart is a subset of a data warehouse, typically corresponding to a specific functional area or department, potentially even to a particular project, depending on how the organization is arranged. So, this follows, in most cases, this is, what happens. Businesses start out small, different departments have different piles of data, right? It's not all necessarily integrated together. They manage their own data in data silos like we talked about earlier, right? But eventually, the goal is to bring it all together. We'll talk a little bit more about that. Now, combining data in one storage system is pretty easy, right? It's like if you got a bunch of crap and you just throw it all in the garage, yeah, storage is the easy problem. Problem is, if you just throw all your shit in the garage haphazardly, it's very difficult to find something afterward, right? And the whole point of storing this data is so you can find it afterward. So, another thing, okay, so two things. Number one, different departments will have different tables with different formats, different permission levels that won't necessarily translate well to other departments. But these days, automating business processes, for example, order fulfillment, tends to require that these separate databases can communicate without human intervention. They can have automated communication. So, one of the big IT trends of, roughly 20, 25 years ago was creating common systems to bring together all these different database systems. So instead of having separate databases for each department or, each national unit of a big multinational corporation, instead, you'd bring it all into one massive common language database so that any query could, in a sense, access all the data from anywhere in the database in the same way, without needing to specially reformat the query for a particular data mart. Excuse me. So, ERP, we talked about that a little while ago. ERP systems are essentially what do this. So they integrate all the data from a business into one common system. The example we had way back when was with the multinational oil drilling operation. So they had all these different national level operations, which had different formats for tables because they were in different languages. They used different kinds of equipment. They used different terms for minerals. Some of them were metric, some of them weren't. So trying to come up with some kind of common language query on all those was a great big headache. Okay, so ERP systems are basically going to transition from that kind of disparate, unrelated databases, bring them all into one common language so that you can run one query and get the same answer from any database in the system. Okay? So, faster and more accurate decisions because you don't have to push those requests through other departments. For example, in this multinational oil operation, you would have to say, find us your 5 best, drilling sites, and when you get the results, convert them into, some standard metric, right? So they'd have to send that, and then humans would have to translate that. Basically, you didn't have an automated process for it. So, the other problem gets rid of ERP. You no longer have inconsistencies across departmental databases. So it's always possible that different departments could have different records on the same thing, and the data would be wrong. For example, your accounting and your finance and your marketing team, they might mention one business, right? But they might have different phone numbers because one of them might have just updated the phone number or one of them might have failed to do the most recent update. And so not all the information is going to be there. Or there can be lag on transactions. For example, a business just placed a big order with you on credit, so you no longer have credit for other things. Well, maybe one department knows that, but until a day or two later when it gets actually processed through all the databases, the other ones don't know that. Okay. So current usage, number one, basically all large businesses these days have an ERP system. Yeah, you can find some that don't, but the vast majority of really big businesses, they do, because the headaches of trying to translate between different formats of different departments is just not worth the trouble. Even these days, a lot of medium and some small businesses do. So ERP is very, very popular. Okay. And again, you know, in Professor Fife's course, they spend like a whole chapter talking about ERP and what it is and how it works and why it's necessary. But these days, all the businesses that need it pretty much have it. So it's just kind of like, it's almost like asking, why do buildings have doors? Well, doors solve the problem of how people are going to get into buildings, right? You could get in through the window, but it's a headache, so all the businesses have doors now. It's kind of like that with ERP. All right. So, last few slides. Supply chain management, one of the things we've talked about, but now we get a little bit of detail. So, supply chain management is fundamentally associated with making sure that goods get to the right places at the right time and in the right quantities. And it also typically involves all those associated transactions. So anytime goods get handed off at one point in the supply chain, there's a transaction or a receipt there. Sometimes it involves money, sometimes it involves credit, you know, whatever. Sometimes it's just a handoff to say, oh, it shifted from this one delivery system to this other delivery system. It used to be on a plane, now it's on a truck. So all those kind of things we lump in together as transactions. And last, tracking data about past, present, future shipments. Basically, looks at what parts of the supply chain are performing well, which parts are performing badly, making decisions around that. So, as a business function, supply chain management has inputs from a lot of different departments. For example, from marketing, what's current demand, what's the trend, is it up or down? That's going to influence how much capacity you need, right? So if suddenly demand is spiking up, well, you recognize, oh man, we got to get some extra shipping capacity because otherwise we're going to fall behind. Accounting, right? Managing all these billings, right? Accounts receivable, accounts paid, all that. And then operations. Operations actually doing the work, actually making the product. So, for example, what capacity is available now to fulfill new orders, right? How much space do you have in the pipeline? And what about over the next 6 months? So if somebody calls in with an order, says, yeah, we want 10,000 bicycles, we're going to sell them nationwide. Do you have the capacity to fulfill that order? And if so, when? All right. So ERP system with high database consistency, right? So if all of the different aspects of the database that might be involved in this kind of thing, if all the relevant data from marketing, accounting, operations, if it's all correct and up to date, then you can get very fast and correct supply chain management decisions. Somebody asks a question, hey, can we get 10,000 bicycles by January 1st? You want to be able to give the correct answer to that as soon as possible. ERP systems will let you do that because it integrates all this data together into one system. Okay, now, supply chain management, migrating it to cloud. For a lot of organizations, supply chain management is a very big application. So, naturally, it's a candidate to get shifted from the cloud. The business says, yeah, you know, we'd like to keep this internal, but we just can't keep up. It's a headache. Sometimes it's really busy, so we need a lot of servers available, but a lot of times it's quiet. And so then we're wondering, why do we have all these servers hanging around acting as expensive paperweights? So ideally, yeah, a lot of times they shift it to the cloud. So give us a scenario. So business manages all its supply chain management processes internally using its own hardware and software, right? That's all under their roof. So the goal, running the same system, but in the cloud, right? But the big problem for this, the supply chain management system can't go offline ever. It has to keep running continuously, even while it's migrating to the cloud, okay? So, big picture process, number one, every component in the internal system, make a virtual clone of it in the cloud, right? So have your application divided into parts, send all of those parts to the cloud to run wherever they're going to run. Okay, so the applications are there and waiting and they're ready to process data. Then, gradually copy all your data to the cloud. And this is going to be a continuous flow. Basically, you have to start off with sending your old data. Okay? Eventually, you've sent all your old data and you start sending the new data as it comes in. At some point, right, pretty much you're keeping a pretty correct copy. Everything in the cloud is going to be the same as everything under your roof. Then, test the component and system functions. You know how it's supposed to work under your own roof. Check and make sure that it functions the same way in the cloud. You get the same results with similar or better performance. Okay? At the end, once you verify the cloud-based system works well enough, then you use it and you shut down the internal system. Ta-da! That's basically how you shift stuff. Okay. Oh, just a couple more slides. So, number one, virtual machines. So, virtual machines, right? If we want to break down the term, virtual means a computerized version of something, right? Surely you guys have heard of virtual reality. And then another one, virtual server. It's not an actual single machine somewhere in the cloud system, but it is the equivalent of a machine, right? So it might be a little bit of server capacity running on many different servers, but the net effect is it's like having a single server. So a virtual machine is the equivalent of a computer, some mix of hardware, software, both. But basically, when you're interacting with it in the cloud, it does all the same stuff that you would expect a computer to do. It's just not necessarily one machine. Okay. Cloud systems built around these kind of virtual machines, right? The nice thing, users don't need to know the internal cloud details. They just say, well, I go to the cloud, my data's up there, the cloud system is going to handle directing me to it. And this gives the cloud flexibility to assign or reassign resources. So wherever your supply chain data is, for example, in the cloud, okay, the cloud wants to put the most popular data where it's easy to get to, and stuff you don't look very often is basically going to push it to the back of the garage. So, because they're built around these virtual machines, cloud can do that. Cloud can say, busy parts of your system, I'm going to install on the best servers I have, or less loaded servers so that response time is faster. Stuff that's not done very often, I throw some cold data back in, again, wherever the cloud says, you know what? You're not going to get the best performance in this part of the cloud, but that's all right because this is data that you're not looking at very often either. Okay, so that's the kind of flexibility that they get. And then essentially, in terms of the user, that means you're going to pay less, right? Because if you're just paying for what you use, well, using those better machines is going to be more expensive. Paying for premium location is going to be more expensive. You just pay for what you need when you need it. Okay. So, supply chain management, powered by Google. So we can imagine supply chain management operations tend to generate lots of data. First of all the transactions that are actually involved, and then all the different performance aspects of shipments. So for any ship that gets taken, first of all, you can talk about the route that it takes, which you can specify in arbitrarily precise detail. If you want, you could talk about every particular street and intersection, for example. You can also look at weather. You can also have like time intervals for every point, like how long it takes you to get from this block to this block to this block. You could have, a very high amount of detail for any one shipment corresponding to, again, a very large amount of data. So, because we know this, because we know that we need Spanner for transactions, right? And we know that we might have a whole lot of data for our aggregate pile of supply chain data, we're going to use BigQuery. So, how we would do this in practice? Well, transactions we run through Spanner, right? We have a high need for consistency guarantees, so Spanner gives us that. BigQuery, well, we don't want to run those big queries on Spanner because that's not really what Spanner is for. It's like using a wrench for a screwdriver. It's probably not going to work real well, okay? So, Spanner's great for that, real-time consistency. BigQuery, if, at the end of the week you want to say, okay, let's crunch all the numbers of this. Let's see which routes did better, which drivers did better, what times of day were least congested, things like that. Yeah, you use BigQuery for that. Okay? All right, so illustrating the difference between the two. Any questions on any of this stuff? Everybody knows everything? That's good. Okay. All right. Well, then that's all I got for you today. We finished up